Hello, all. Welcome back. Today, we'll be talking about the next section of the module, namely frequency synthesizer, wherein we'll be talking about the oscillator model. So, the flow is like this. We'll be describing phase noise. Then, we'll be talking about the oscillator noise model. Then we'll discuss about Leeson's model, and then we'll go to the phase noise properties. So let us talk about phase noise in oscillators and PLL. So the causes of the spectral purity degradation are due to the various noise that is introduced by the elements in the system. So, for example, in a PLL, you have the phase detector, the loop filter, the VCO, then there are various other elements in a VCO, the tank circuit. Now, all of these elements will be responsible for their inherent noise, which in gets into the entire system and degrades the performance. Not just that, so we do not have idealistic responses of systems, and you have seen in the DDS where there are some spurious sidebands which are present in the real world scenario, which are not thought of in the ideal response, but they do exist and they have absolutely no harmonic relationship and they create noise. They are responsible for adding noise in the system. So, what is phase noise? An oscillator is intended to generate a well defined reference frequency in the frequency domain. So, any disturbance from this reference ideal behavior is an undesired phenomenon and it is called phase noise. So, here you can see the spectral purity is important, and what I want to show you in this slide is ideally we would want to see this kind of an impulse response from the oscillator, but that is not so. What we see is the real oscillator spectrum has some sidebands, and this is how it appears to be. So, what happens in the process? So, take an example of a receiver system where the RF signal is received along with another undesired signal. So, here you can see, unfortunately, the desired signal is of a lower amplitude, whereas the undesired signal, which appears very close in frequency to the desired frequency, it is not just close to it in terms of frequency value, but its amplitude too is much larger than the desired signal frequency. So, what happens in the process? These signals, which are then down converted, you know that a mixer has a oscillator, and so the signal is mixed with the local oscillator signal frequency and the RF frequency, and you can notice here now our LO is present, and the LO seems to have a response like this, which is having some sidebands around it. So, though the received signal is kind of shown in the form of a impulse form, but our local oscillator seems to have a response like this. So, what happens in the process is that when these two signals are mixed and down converted, what happens is both these signals also will get mixed with the LO, and the down converted signal will have the IF of the desired frequency, and next to it, because they were close in the higher frequency range, they too will be close back again when they are down converted. And since the response of the LO exists, and it will multiply with the undesired signal too, and causing the undesired IF also to be present. Though it seems that the low pass filter should now do a good job in filtering out the undesired signal, leaving behind the desired IF, yet there could be problems when you have a receiver working in various channels. Now you notice that the desired IF may fall into one of the channels, whereas the undesired IF, which is not what we want, could fall into the adjacent channel, causing problems. So this kind of a response, which is not desired, you know now why it is not desired, is because it can cause such problems of interference in the adjacent channels. So, what we will learn today is about the mechanism behind phase noise generation in oscillators. Of course, we will apply analysis to the prototype circuit. It holds good to any sort of harmonic generators that are present today. We will be dealing with noise generated by the LC tank, also dealing with noise generated by the active part or by the source. So, as you know, an oscillator has a active part which generates the negative resistance, and the tank circuit which selects the frequency of resonance. So we'll be taking this model as our prototype, and you can see this is the LC tank circuit. We'll be talking about the noise introduced by the LC tank, and also looking at the noise of the transconductance. The quality factor of the LC tank can be understood to be 1 over omega naught L GTK, where GTK is the conductance of the LC tank circuit, and it can also be expressed, the quality factor can also be expressed in the form of the capacitance. Now, in both the cases, I mean, you have to understand that in the ideal form of things, the GTK does not exist. But in reality, there will be certain amount of loss, and which will hamper the quality factor. So if I would want to have a very high Q, then I would look for elements which will offer very low losses. So let us discuss the linear phase model of uh, of the circuit given here. There are noise sources. How will they propagate across the LC tank, and how that adds to the noise generated by the LC tank itself. So let us look at how much noise does the LC tank itself contribute in the oscillator, followed which we will look at the noise contribution of the active part. So any harmonic oscillator, especially those that are based on the resonator that is being undamped, can be configured as the following with LC tank. The tank conductance GTK. In order to keep the oscillator going, there should be an undamping circuit, essentially minus G, that is the negative resistance. It must be greater than GTK. As soon as that condition is fulfilled, this circuit will oscillate. So what happens to the noise source present in the oscillator? There will be noise generated by this GTK, and that noise will be filtered by the LC tank. Then it becomes phase noise. So phase noise in essence is filtered noise, and it is filtered in a special way. Likewise, the noise contributed by the active part, the noise that takes shape in the form of a current, filtered by the LC tank, converted into voltage that will be added to the oscillator signal itself. So there is noise by the active part, which is filtered by the tank, and the noise generated by the tank itself. Now both these noise, the noise from the active part and the noise from the LC tank, have a superposition, and they superimpose themselves on the oscillating signal at the output port. Due to this, we will witness certain amount of shaping called phase noise, the shaping that we have seen in the previous slides. So it is not like an impulse function, but it forms a shape. So the noise shaping that occurs by the LC tank can be calculated from the tank impedance. So if we look at a certain distance delta omega from the carrier frequency, which is not a desirable thing to happen. We would not want to have a delta omega provided it is an impulse function, but since it has a shaping, there is going to be a delta omega. So a certain distance delta omega from the carrier frequency, we can calculate the tank impedance, and then you can find various expressions, since you can express them in the form of capacitance, or you can express them in terms of inductance. So you can see the tank impedance. expressed at a certain distance from, from the carrier, we can see that the tank impedance decreases when the offset from the carrier in frequency increases. There is an inverse relation. So it makes sense since at resonance the tank circuit has GTK as the conductance, and if the carrier frequency shifts, then it is either L or C, as whichever dominates. So the noise injected into the LC tank will be converted into a voltage across L or C. In order to calculate its value, we need to multiply the power spectral density of that current source with the square of the absolute value of the tank impedance, and the square is important because we are dealing with power. So you notice that this is the impedance, and the square of the impedance is taken. So you can notice that the absolute value of this complex impedance is given in this form. The noise power that is per hertz that is injected into the LC tank will be converted by the LC tank impedance to the absolute value squared into folded square per hertz. So here we have the expression of the complex impedance of the LC tank at a particular offset from the carrier frequency omega naught by squaring this term, taking the magnitude of that, multiplying with the injected noise current square per hertz, we end up getting voltage square per hertz that is appearing across the LC tank. That is why the square of the absolute value of the tank circuit impedance is important, because that is the basic mechanism that will convert the noise current into noise voltage. So you have this noise current injected into the LC tank by the LC tank converted into noise voltage. So we have denoted the noise voltage in the LC tank as VGTK square. This is the power rather, not the voltage, but the power representation, the noise power by the LC tank. It is also possible to rewrite the tank impedance in terms of quality factor. So this would be the quality factor, and so you notice that higher the Q, better is the output from the oscillator. Noise free, more is the Q, uh, it is more likely to be noise free. Noise shaping means that the conversion of noise by the tank circuit, of the white noise generated by the tank circuit and active part, into colored noise or frequency filtered noise due to the tank impedance. In case of the active part, minus G part will be added in parallel to the noise of the tank conductance and thus be filtered in exactly the same manner. For oscillations, it is important that the actual value of G is greater or equal to GTK. So we can say, well, so that one portion of the noise added by GTK and the rest is added by this active part, we can define a certain noise factor. So, this is the noise factor by the active part. A stands for the noise generated by the active part. Generally, A is related to minus G. Ideally, A is 1. This is a case when the oscillator is at the edge of oscillation, that is minus G equal to GTK. Generally, you require a little bit more of negative conductance in order to keep the oscillations going. And that mainly is the reason for the noise to be generated. Not all the noise sources are on all all the time. They may be off for some time. So noise that has entered into the tank will be frequency shaped and will be band passed filtered around the carrier frequency omega naught. So you can see that the noise generated is the largest around the center, around the carrier frequency. Since so if delta omega tends to 0, you will see that this noise, which is a reciprocal of delta omega, goes to infinity. So the problem is that the noise is present not away from the carrier but closer to the carrier or closer to the center frequency. So phase noise is basically the reciprocal of carrier to noise ratio. It says something about how much energy do I have at the carrier exactly and how much energy do I have close to the carrier. And ideally this carrier to noise ratio we would like to have as large as possible. I'm talking about carrier to noise ratio, not noise to carrier. So we have the total noise power here as Vn total. We have the signal power, and if we assume a sinusoidal signal, and that is a realistic thing because the LC tank does perfect filtering, the current generated by the active part. So we have the sinusoidal signal appearing across the LC tank. Then its power is Vs square by 2. So this noise to carrier voltage ratio, noise to signal, rather this noise factor, which is nothing but the ratio of these noise power to the signal power. You can see we have taken Vs square by 2 is because we are dealing with sinusoidal signal power, and since it's harmonic sync function, so we have put a 2. So with noise there is amplitude and phase. So the total noise is just half of it. So there is a half here, and there is a half here because we are dealing with a sine function, sinusoid, and there's a half here because we are dealing only with phase noise. So by definition, the phase noise is proportional to noise power and inversely proportional to signal power. And this is the factor, noise factor, where you have the contribution from the LC part as 1 and the contribution from the active part as A. So we can derive expression for phase noise, and if we talk of signal power, this is what we have. So this is the phase noise in the oscillator model, and so phase noise is always described a certain distance from the carrier. So if people talk about phase noise, they must tell you the carrier frequency and delta omega, that is, at what distance have they calculated or simulated the phase noise. Otherwise, there is no meaning. There is no such thing like constant phase noise. The phase noise is directly proportional to the noise generated by the LC tank, and it is also directly proportional to the noise generated by the active part, and it is inversely proportional to the square of the quality factor. And this is the reason why designers would prefer to have high Q oscillators when they are looking for good oscillators. So the quality factor is good, then you have a very good oscillator. So that means the quality factor, which is decided by the LC tank, is important. So they choose LC tank circuits uh, such that the Q is high in order to have a low phase noise. So we use Leeson's model, phase noise uh, model. It has a slope of minus 20 dB per decade. The only way to compare oscillators running at different frequencies is to take this difference in frequency into account, and people have defined so-called phase noise to declare power consumption figure of merit. So I'll be talking about that. So you have seen in this expression that the quality factor and phase noise is inversely proportional. It is also inversely proportional to signal power, and because of the presence of the square term, we'll see that in the next slide, that at mid frequency there is a slope of minus 20 dB per decade for the phase noise, and the phase noise is directly proportional to the square of the oscillation frequency. Now coming to the figure of merit, it compares the phase noise at a particular distance. So here is the figure of merit. You can have a look at it. So for every oscillator away from the carrier frequency, the phase noise becomes smaller. Of course, the phase noise is much larger near the carrier, and as you move away from the carrier, the phase noise goes lower. So then when we multiply the distance from the carrier divided by the carrier frequency square, and then multiply with the power, we get a figure of merit. So an oscillator that consumes less power will suffer from less phase noise. So the figure of merit allows comparisons of various LC oscillators, and generally the phase noise that we talk of is around minus 140 dB. So here is the phase noise plot. If you have an LC oscillator and if you zoom into very close to the carrier is here. The phase noise plot has several regions. One region very close to the carrier, you will find the slope of the phase noise is around minus 30 dB per decade. In Leeson's phase model, at mid-band predicts minus 20 dB per decade. That is because of the white noise is being filtered by the LC tank. This white noise that is filtered by the LC tank causes this minus 20 dB per decade slope. And apart from minus 20 dB per decade, we also have a region where the noise configuration is flat. So this is due to the other elements, active elements in the circuit. The minus 20 dB per decade in the phase noise is explained using the LC tank, which we have seen in this slide here. So in both the cases where the noise from the active part and the noise of the LC tank, both of them which are filtered through the LC tank has this square term, because of which you will notice that there's a minus 20 dB per decade slope here in the frequency, the phase noise plot. While the minus 30 dB per decade is explained due to the 1 by F noise, the flicker noise. So there is 1 by F noise generated in the active part. So mainly these active parts, which are sources, the transistors, they switch on and off, and because of which they introduce the flicker noise. And if the active part starts switching, then what happens is that the 1 by F noise that is close to the DC is being up converted to the oscillator frequency. If we experience the slope of minus 30 dB per decade, the only way is to explain is by the presence of the flicker noise. So if a very low frequency oscillator is designed, usually near the carrier frequency, you will not experience the 1 by F noise. So straight away you will see a slope of minus 20 dB per decade. So and this flat noise is due to the various elements which are instrumentation elements and active elements. So there is a modification in the Leeson's model. Here you can see that the axis here shows that the noise dips lower, quite far away from the carrier frequency, and which is around F0 upon 2Q. And if we have a quality factor which is very high, then what will happen is that this term will be lower. That is to say that the phase noise would go lower much quickly, that is very close to the carrier frequency. So if this is the carrier frequency and I had a very high Q, then this phase noise, which is the lowest that the oscillator is experiencing, would be closer to the carrier frequency. And of course, you can see here the corner frequency for the flicker noise, say 1 by f cube, and rest of it is flat noise. So thank you, and we will continue with the next section of the noise model of the PLL.